Adam, the teleprompter's not working. Shit. Oh, I guess I'll just wing it. Sorry, that was pretty bad, come on. So how are we all doing? We enjoying the heat wave? Come on, it's lovely. So as you may have guessed, I'm Dale Anderson. A bit of background about myself. I've been in the industry for about 13 or so years in a huge variety of roles. Sort of started in network admin, but the majority of them have certainly been development on the Microsoft technology stack. I quit my full-time job a couple of years ago to start work on a product which was in the sporting industry, and the product that I'll give you a demonstration of later on in the second half of the presentation is actually a result of that process. The product hasn't actually been released yet. I ran out of money and had to go back to work, unfortunately, but development on the Tribe platform is definitely continuing. So I'll give you a run through that later on and hope you like it. So there's going to be two sections to the presentation. I'm going to run through a little bit of theory first up. I'm going to try and get through that as quick as possible so we've got a little bit more time to spend on actually demoing the platform. But we're going to talk about, just to make sure that we're on the same page, we'll put a few definitions around scalability and sort of what that looks like. We're going to talk through a couple of different consistency models, the ACID transaction model, etc. And we're going to look at some message-based architectures. You would have seen CQRS was on the blurb for the talk. We won't spend very much time on that. We'll just sort of generally talk about some key concepts in message-based architectures, and then we'll move on to a demo. So what are we talking about when we talk about scalability? There's two kinds of scalability. We're talking about vertical scalability and horizontal scalability. So your vertical scalability is when you have a system that is housed on, to simplify things, a single machine. So how many users can we get out of that application from a single machine? And as you can see from this graph, as we increase the number of users, we get a fairly consistent sort of response time until we start getting a lot of resource contention in our system, and then the response time actually starts ramping up very quickly at that point until we get to a certain point where we get timeouts and general sort of non-availability. So let's talk about horizontal scalability for a minute. Obviously this is going to be about scaling our system out across multiple machines. So ideally, what we would like is linear scalability, so that if a single server can handle 1,000 users, if we have 100 servers, that means in theory we should be able to support 100,000 users. Doesn't quite work like that in practice. That's virtually impossible. It sort of looks a little bit more like that, where the number of resources, the number of servers that we actually need to serve those requests starts ramping up a little bit faster as well. So we're going to look at some of the things that impact our scalability, both vertical and horizontal scalability. And I would be willing to bet that everyone in this room has used the ACID transaction model before. Every major database vendor, relational database vendor at the moment uses the ACID transaction model as the underlying transaction model. So what is ACID? ACID, atomic, consistent, isolated and durable. And I'll just run through those very briefly. Atomic is to make sure that if you execute a transaction, either all of that transaction commits or none of it commits. So if we get halfway through a transaction and that fails, the transaction rolls back and the database remains in the same state that it was in before you executed that transaction. Consistent, so this ensures that your data is in a valid state according to the rules that you've declared, both before and after the transaction. We're going to talk a little bit more about, or a fair bit more about consistency as we go through. Isolated means that your transactions execute as if they are the only transaction executing in the system at that time. There are a number of different isolation levels which you've probably seen in SQL Server, and we'll talk a little bit about isolation levels and how they can impact your vertical scalability. And durable means that once the transaction has committed, it can survive power failures. So it's been committed to a persistent storage medium. So how do we achieve ACID transaction? Well, the database needs to take out locks on certain records. So if we have a transaction that might involve, we'll actually look at a simple transaction here. If we have a transaction which has a couple of select statements in it, and another transaction that's operating concurrently with an update statement, ideally you want the same data returned from the first two select statements. The default SQL Server isolation level is actually read committed, and the second query will not return the same value because it's been updated by that second transaction. So if we were to use a serializable transaction level, what SQL Server will actually do is it will take a read lock out on that record, so the other transactions can read that, but no updates can be made to that record. So our second transaction there will actually be delayed from committing until that second select statement executes. So we're starting to build up this contention between our resources, and this, I'm sure you can see, if we have a serializable transaction level, we've got a lot of concurrent reading and writing of the same records. It's going to impact the amount of time that it takes to return from those transactions. In certain situations, SQL Server will actually also perform what's called lock escalation, where it will convert a number of very fine-grained locks into a chunk of, it locks a whole chunk of your table. It does this to conserve resources, but obviously this is going to increase the sort of resource contention that we were talking about just before. Deadlocks is probably not a major scalability issue, but if deadlocks can occur, and that's another problem which can cause, can reduce your vertical scalability. So vertically, significantly impacted by your isolation level. You're going to be able to support much fewer users vertically on a same server if you use a serializable transaction level as you would from a lower one. So what about horizontal? How can we split our SQL Server database across multiple servers? And there's a couple of options for that. The first is replication. Generally reserved for disaster recovery scenarios. The overhead of keeping more than one database synchronized at the same time, well, we need to have transactions across those two databases. If we are introducing network latency into that transaction as well, it's a recipe for disaster. So replication for scalability purposes is really not an option. Sharding, on the other hand, is breaking our data up into categories and splitting those categories across multiple servers. So we could split our customers up by the first letter of their surname, or we could break it up by geographical location. So let's think about some of the issues that we might come up against if we're going to shard our data. Well, our customers are going to be referencing some common data across each server that we shard to, so there'll be this common data. Now we need to keep that data synchronized across those servers that we've sharded across to make sure that that's kept consistent. So there is a cost there. We're reducing the consistency of our data to improve the scalability. There's an overhead in making sure that that common data is kept synchronized across. And this leads us neatly into a theorem called the CAP theorem. Many of you may have heard of this theorem before. It was a conjecture originally made by a very smart guy called Eric Brewer from the University of California at the 2000 Symposium on Principles of Distributed Computing. That was a mouthful. Later in 2002, two other very smart people, Seth Gilbert and Nancy Lynch, published a formal proof for it. The proof has been contested, but the basic premise of the CAP theorem remains the same. So what is the CAP theorem? Consistency, availability, and partition tolerance. So when I talk about consistency, basically consistency, if you think about the ACID transaction model and the consistency that gives you in that your database is, your data or your system is in a consistent state at all times. So that's what I'm talking about when I'm talking about consistency. Availability means that the system will guarantees that it will return you a response, either success or failure, for every request. And partition tolerance is the interesting one. What are we talking about when we're talking about partition tolerance? So the CAP theorem states that we have a replicated service. So we have, in theory, two servers that are being kept in sync by some process that synchronizes the data across the two. So this is all happy. We've got consistency, we've got availability, both servers are responding, and we've got our partition tolerance. But what happens if the network link between these two servers fails? So we're obligated to provide a response. We need to make sure that these servers are available, but the data that's returned by those two servers necessarily is going to be different. If there's updates provided to one of those servers, the second server isn't going to see those. So you can see that the theorem is basically saying that we can only have 2 out of those 3 properties. If you want consistency and availability like you would in a normal relational database setup, you can't have partition tolerance. So which one of these are we going to sacrifice? Well, we can't sacrifice availability. We want our service to be returning something the whole time. So we want to partition our data. We want to achieve that horizontal scalability. So the only one left is for consistency. And this brings us to a consistency model called eventual consistency. Most systems that use the eventual consistency model operate under a consistency model called BASE, which is basically available, soft state, and eventually consistent. So basically available is what we were talking about before, about every request receives a response, either success or failure. Soft state refers to only cached data. Generally, if you're talking about a system which is soft state, usually that system will be stateless, but we can allow cached data into that as well. So we're not allowed to maintain things like session state that you would on web forms or something like that, perhaps. So you're not allowed to store any state on that server. And it's eventually consistent. So what are we talking about when we're talking about eventually consistent? Let's think about displaying stock levels. We have an online shopping site and we have a number of products. Very high volume site, we get a lot of users. Every time someone places an order, obviously the stock level is going to go down. But do we really need to display to the user that there's 4,972 units left in stock? Are we going to make them wait that extra 100, 200, 500 milliseconds just to display on the page that there is so many left in stock? I don't think so. And if you think about most of the user interactions or user operations that take place in an application, there are a significant number of them that we could actually, okay, we don't need to necessarily update our data or display to all of our other users the exact value immediately. We can introduce a delay into that. We can have it eventually consistent. So Newegg, for example, here doesn't even display a stock level. They just display in stock. You might remember on eBay they display, I think, 10 or more available. So if we take that as an example, if it says 10 or more available and we're getting an order, say, every second, then we want to make pretty damn sure that we update that within 10 seconds. Does that make sense? So if we're getting an order every 10 seconds and we're displaying 10 or more of it left in stock, we want to make sure that we update that number left in stock within 10 seconds. Otherwise, we're going to get orders coming through and there isn't going to be anything in stock. Now, I mean, on the surface, it might seem like this is a really bad thing. A user's ordered something, we don't have any in stock. But, I mean, at the end of the day, is that really an issue? We send them an email, sorry, your item's on back order. We can actually even make a decision about which customer we inconvenience in that case. Our VIPs or our preferred customers we don't want to inconvenience, so we'll make sure that we send them out an item that is in stock, and we can inconvenience maybe someone who's just returning for the second time. So in this case, we have eventual consistency on our stock levels, on our inventory. Another example of eventual consistency airlines issue a number of airline seats to sites like Flight Centre, etc., but they're not going to give Flight Centre their own allocation on each flight. That just wouldn't make any sense. So we can't actually guarantee that that seat on that flight is available. They may all be booked out. There's no way to guarantee that these resellers have the accurate information that they need up to the point. It's not until we actually go to book that flight that it actually performs a check at that point. If we had to perform that check every time we displayed that page, well, I think you can imagine that would be just an extremely slow web page. So if we're not going to ensure that our data is updated and is consistent at all times, there's an alternative sort of architecture that we can take, and using messages instead of sort of a synchronous request response every time we want to do an operation, it gives us a lot of flexibility. So generally in a message-based architecture, we're talking about two different kinds of messages. We're talking about events. So an event can be defined as a significant change in state. So a user purchased an item, could be an event that he's just sent out. Now we don't expect a response to this, we're just telling the world that this happened. The other kind of message that we're going to be sending is a command. So this is an asynchronous request for a specific action to be performed by a receiver. And this is probably actually a better example for a user placing an order is probably more likely to be a command. But the key thing here is it's an asynchronous request. So we send off the fact that our user has placed an order. We expect that to succeed. We don't expect a response from the server. So asynchronous is very important, and the fact that we don't expect a response. So one of the things, or a few of the things that we need to make sure of in a message-based architecture is guaranteed delivery. When we send this command over to the server, we need to guarantee that that message will be processed at some point or another. And that's something that's usually provided by the infrastructure. N-service bus, for example, once you publish a message, you can guarantee that that message will be processed. Error handling in message-based architecture. So we're talking about genuine exception conditions here. A bug in the code, persistent network failure. And what happens if that occurs is we'll put that message onto a queue or a holding area, and we can replay that message later. So instead of making a synchronous request to a server, so a request response paradigm, if that fails, we don't have the ability to replay that later. Whereas in a message-based architecture, if an exception occurs, we can simply take that message and put it back on the queue that it was supposed to be on, and we can recover from that at a later date. It's worth talking about transactions within message-based architectures as well. Clearly, if we have a user operation that's going to result in a number of changes to our data, it's going to be, we would like, so we're updating data source 1, then we want to update data source 2, but that step fails. We really want to be able to either roll back the changes to the first data source, and Microsoft provide MSDTC. I'm sure everyone's heard of MSDTC, the Distributed Transaction Coordinator. Generally results in quite a slow system. For the reasons that I talked about before, introducing network latency into a transaction is generally a bad idea. So what's an alternative to distributed transactions? There's a concept called idempotence. So what is idempotence? Idempotence is the property of certain operations that can be applied multiple times without changing the result beyond the initial application. So what we're talking about is if we process a message, the first time it's processed, it'll have the desired result. If we then try and replay that message, nothing will occur. Your system will remain in the same state as it was after the first time. So how does this help? Well, if we go back to updating our two data sources, if we have a message, we update our data source, second one fails, okay, so that goes into our error queue. We can then replay that message, first update our first data source. Because we've already executed that message and updated the data source, nothing happens. Then we can apply the update to our second data source so our system remains in that consistent state. Now, idempotence is not possible to achieve in every situation, but it is a very highly desirable characteristic of message-based architectures. And one of the very, very key things about designing message-based architectures is we need to start thinking about our user interface design a little bit differently. If we're displaying sort of simple forms onto our screen and then just posting the contents of that form to a database table, that doesn't capture actually what the user wants to do. So we might have a customer form which has got a checkbox on it that says this is a preferred customer. So we got a save button on there. If we simply post that chunk of data back to the server and persist that, we're not capturing the fact that we actually made that user that customer a preferred customer. We'd have to do something like perform a difference, some sort of difference on the previous state and the current state to actually figure out that the user changed that customer to be a preferred customer. So we need to start thinking about how we design our user interface to capture the intent. So we might, instead of a checkbox to mark our user as a preferred user, we might have a button there that glows when they're already, or has different text on it, and for whether they're preferred or not. So when we click that button, we're actually capturing the fact that we want to make that customer a preferred user. And it's a very key part of designing your interface. You need to capture the users, what the user is actually trying to do. One of the big advantages of message-based architectures is that it allows us to prioritise the different user transactions. If we were in a traditional sort of system where we've got a service layer, we can't assign more priority to each of the requests coming in. Whereas if we're publishing messages and putting those onto a queue, we can separate those message types into different categories and assign additional resources. So we might have a queue for customer orders, we might have a queue for incoming deliveries or something like that. Obviously the customer orders are going to be much higher priority. Let's throw 10 servers of that instead of one. And Azure gives this really cool ability to add more instances automatically, and we can actually wrap each transaction within a particular SLA. We need this transaction to complete within 10 seconds, like I was talking before with the stock level. So we can actually assign SLAs to individual user transactions if we would like. So I'll talk very briefly about CQRS. I know it was sort of maybe a focal point of the blur, but I'm only going to talk about it very briefly. I really want to get onto the tribe stuff. But what were the driving forces behind CQRS? It's exactly what we were talking about before, collaboration, where we have a large number of users that are reading and writing the same set of data at the same time. The sorts of things that the ACID transaction model really struggles to cope with. And also staleness of data. And if you think about it, any web system has a degree of staleness in it. So we've retrieved our data from our database, we've displayed it on in the browser. That data is already stale. Some other user may already have come in and updated that user. So every system has a degree of staleness. Once you start to introduce caching in particular, caching introduces another degree of staleness. So we need to handle the fact that our user might not have the most up-to-date information. And traditional sort of architectures don't tend to deal with this problem, that the user may have submitted a request on incorrect data. So what does CQRS look like? The most important thing about CQRS, and probably the key thing, is we have a separate read and write model. So you can see there's two data stores on that diagram there. The lower one is what we can call our authoritative source. So that's our write model. The one up the top there, which is labelled cache, we'll talk a little bit more about that. That's our read model. So whenever the user is executing a query, we're actually retrieving our data from a cache instead of our ACID transaction model database. So these AC things, they're autonomous components. Basically, they're systems that will operate autonomously. So we can choose the technology. We use the technology of our choice in our write model. We can still use ACID transactions within that model. Because we're doing this entirely asynchronously, it's not going to have any impact on the user's experience. So we can still use relational databases there. But we've got a lot more leeway in how we structure our data in the cache. So we might have a number of view models on our UI. Let's structure the data in our cache to be a one-to-one correspondence between our view models and our tables. So it's very low latency. We don't have to navigate any relationships. We don't have to worry about people updating this constantly. It's just a single record in a table that matches our view model one-to-one. Very fast. We can use NoSQL databases. We could use the file system if we liked. So this is a very good way of dealing with this resource conflict, the collaboration problem that we've been talking about. Another message-based architecture that's becoming increasingly popular that you may have heard of is event sourcing. So in event sourcing, basically we want to capture all changes to our application state as a sequence of events. So instead of each time request response, we're going to post this data or retrieve this data from the database. Instead of doing that, we just want to publish an event. So what does this actually give us? I mean, the most obvious, of course, is that we've got a log of everything that happened to the objects in our database or in our system. Kind of useful, but definitely not the biggest benefit of event sourcing. Event sourcing gives us the ability to, we can take our blank object and we can rebuild that object from the events that have occurred against that. Because we know all of these events, we can just simply replay those and rebuild our object. We can perform temporal queries so that if we wanted to know what our object looked like 10 minutes ago, 2 years ago, all we need to do is just replay those events up to that particular time, and we get this ability to see what the state of our system was at a particular point in time. An event replay, of course, is related to those two, but we can actually replay the events on a user interface at the same time as well. So to use perhaps a cricket game, for example, every time a ball is bowled, the umpire, they may score 2 runs, they may get bowled out, etc. We can actually have a user interface. We can replay those events through it so we can see the game at a later date. Reversing events is quite useful within event sourcing. So we're talking about, okay, maybe that last ball that they bowled, they ran 2 runs, I recorded 2 runs, but actually I was wrong, they got run out. So we need a way of reversing that previous event. And we can do that either by completely rebuilding the object from scratch. If there's been a lot of events, obviously this is going to be quite an expensive operation. We can implement reversal methods for each of our event handlers, which is quite common. Obviously there's going to be a lot of overhead actually implementing those methods. So when we're reversing the 2 runs that they scored, we need to decrease the total by 2 runs, decrease the overcount, etc. So it can be quite expensive, but it's obviously going to be the most efficient way of reversing those events. There's kind of a middle ground. So an epoch is I think the definition of epoch is a significant moment in time. And what we can do is we can take a snapshot of our object at particular points in time. Maybe it's every 10 minutes, maybe it's every 10 messages, and we store the state of that data. But we continue to obviously build up our event logs so that if we wanted to rebuild our object, if we've had 1,000 events, we might have an epoch that was 10 events ago, so we only need to grab the state of that object from the latest epoch and then replay those 10 events rather than 1,000 events. So it's kind of a middle ground between completely rebuilding and the reversal method. So Tribe is definitely what you would call a composite UI. Composite UIs are quite suited to message-based architectures for a couple of reasons. But I'll go through what a composite UI actually is. So the composite pattern simply states that a group of objects can be treated the same as a single object, and that we compose these objects into hierarchies. The composite view pattern is a recursive UI structure of views containing children that are themselves views. So to take that a step further, we might have a view that contains a number of child views, but we can deal with any of those views in the same way. We have a consistent API for accessing those views. For example, this is actually the Tribe.js website. This was written in Tribe, of course, but we can see that this page is actually composed of a number of child views. So even the example that's being displayed here, so we've got our header up the top here, which is a component of its own. We've got our menu bar down the left, and we're displaying this example here, and the example itself even has components. So we can actually take that component and we could display it on the screen. We can deal with that, treat that exactly the same, regardless of what level in the hierarchy it sits at. The final piece of the puzzle as far as composite UIs, many of you have probably heard of the MVVM presentation architecture before. It originally came from Microsoft as a specialization of the presentation model. I mean, MVC, etc., are all specializations of the presentation model, but this is a specific. So MVVM simply means model, view, model. I think it's pretty clear what a view is in that context. I think it's pretty clear what a model is in that context. So the model represents our view of the world. But what's a view model? So a view model is a value converter. Our view model is intended to sit as a layer between our view and our model. So it exposes objects from the model in such a way that they're easily managed and consumed. So rather than displaying this highly normalized model to our view, we can convert that into a much neater representation that matches our view much closer. So it gives us that layer in between to assist us in managing our model. A key component of MVVM is data binding. I'm sure you've all come across data binding before. It necessarily needs to be two-way, so that if we have a piece of data that we're displaying on a screen, we need to make sure that if we change this data in our view model or in our model, that gets represented on the UI, and vice versa. If we change that on the UI, we want that to be pushed back to our model. And this is done through a concept called observability. So instead of a standard property on our model, we declare it as an observable. And that observable then gives notifications. So this is actually from the Knockout.js site, and this is quite a good example. If we look, we can see we're declaring an observable here, the chosen ticket, and that's what we're displaying, that chosen ticket. I'll actually bring up the Knockout site. Okay, so we've got choose a ticket class, we've got a drop-down box, and you can see that these various options that we provide change the behaviour of that. And this is our view model down here. So if we choose a ticket, it displays that there. So I hope that makes sense, and that observability, as we make changes to this chosen ticket variable, the changes get reflected in the UI immediately. So if I change that, the changes get reflected immediately. So that's our data binding at work. Any questions? Just quickly before we move on to the demo? Good. So I'm just going to quickly create a little Visual Studio project. I was really hoping to show you a new IDE out there called Cloud9. Probably going to be making a pretty significant investment in it fairly soon, but it's entirely hosted within your browser, hosted within the cloud, so you can access your code from wherever you are. And the editing is, you might think it's not going to be as good as having a native client. It's awesome. It really is good. But unfortunately, I didn't have time, so Visual Studio it is. Familiar old Visual Studio. So we've created this project called Project 1. Let's install Tribe. All we need to do, npm install Tribe. And that will go off to the npm package manager. Of course, you need to install Node before you can access npm and Node itself. Very painless. Windows, Linux, the installation process is very straightforward. Okay, so we now have a Node modules folder here. And Node actually gives, Tribe gives you an installer. If I run that, basically what this is going to do is just copy some templates over to our project directory. So let's install. And we've now got a bunch of folders here which we can, add into our project. The only ones I'm going to be concerned about for now are these panes, sagas, and the server. So Tribe is focused around the concept of a pane mostly, the composite UI. So a pane is what we were talking about before when we were looking at the components of the Tribe.js. A pane just simply represents a single component. So if we look at, it'll give us a simple layout. All it says is welcome to Tribe. So let's start up our server. And let's have a look and see. Runs on 1678 by default, just for development purposes, but obviously that will be configurable. So not very useful just yet. Let's have a bit of a tinker. So Tribe will expect a pane called layout. And all we need to do to create panes, we don't need to worry about an index.html and any script tags to include all of these or loading our templates. Tribe takes all of that pane away from you. All you need to do is just in this panes folder, we can just add a new JavaScript file. Call it the name of the pane that you're working on. And there's just a simple little register model that we need to call to register our pane. So let's start putting together, I'm going to build a very simple little chat program. So let's get stuck in. So let's have an input. And here we're going to start doing some of our data binding that we talked about before. Can't read it? I'm sure I can zoom here somehow. No better? Let's add a button. We're going to call into a function called send. And we're going to have a list which is going to go through our messages array. So in here, I'll explain this var self equals this in a second. It's a kind of peculiarity of JavaScript that I'll explain in a second. So let's now expose our properties that we were talking about as observables. And for our messages collection, we're going to use an observable array. Okay, so one of the key things about Tribe, as you probably would have read in the blurb, it's really focused around reducing friction. So we don't want to have to re-minimize or recombine, even restart our server. All we need to do is just refresh the page, and any changes that we've made to that, they automatically get combined and minified for you, and then they'll get served up for you the next request. So we don't need to worry about any of that sort of stuff. So it doesn't actually do anything yet. Let's publish a message when we send, oops, pane pub sub, publish so here, this is where our self variable that we declared up here comes in. This works a little bit differently in JavaScript. Whilst this send function is executing, will actually resolve to that function itself. So the scope of that changes. So we need to hold on to a copy of the this. So this, in this case, actually refers to the instance of the object. This, while this function is executing, will be this send function. So we can hang on to that. Okay, so we're publishing a message. The only other thing we need to do is subscribe. And if we go self, messages, push, message. If we refresh that, and we now, oh god damn it. I think this is, I have to probably mention at this time, the server-side component of Tribe is a prototype at this stage. There are definitely some issues with it. The client side, the composite side of things is production ready. That's actually being used in a number of sites already. Okay, so we're now getting our messages being published and subscribed to, and they're displaying in our page. Not really very useful. It's only running locally. So let's see what we can do about that. We're going to create this thing called a channel. We're going to call it a chat channel. And the key thing here is I'm going to call connect. And what that will do is connect our channel to the server, and any events that we then publish over that channel will be broadcast to any other users. Okay, so that all still works. Let's open up a second window. And start sending those messages. Oh, are you kidding? I think there's something that's not quite working properly with the rebuilding of it, but that will certainly be resolved. Okay, so we're now getting our messages being published seamlessly across any client that's connected to that channel. So it makes distribution of these messages really quite simple. So in any good single-page application framework, we need to handle navigation between different panes. So what I'm going to do here is I'm going to rename this to be chat pane, and I'm going to add another layout. And what we're going to do in that layout is we're going to choose a channel that we want to connect to, so we can have multiple chat channels. So let's add another item, HTML layout.htm. So let's have a field for username, username, and one for channel. And another button which we can click to actually join that channel. So click join. Give it a label. Yeah, sorry. Okay, so let's set up these properties. Damn IntelliSense. Okay, this dot username, and this time we might give it a default username anonymous, channel chat, and this is a function which gets called when that button gets clicked. We need our self variable again. So now all we need to do to navigate from this pane to our chat pane is just simply say pane.navigate chat, and we can pass it some data. So let's say username is self username. So the thing with observables is they're no longer standard properties. We actually need, they actually expose a function. So we need to execute that function to get the value out of it. And how you set an observable property from code is like that. So that will actually set the value of that observable to test. We just want to retrieve it in this case. And for our channel, self.channel. So we just need to make some quick changes here. So the data that gets passed in is exposed through our pane.data property. So we can say channel right there. And now when we push this message on, when we publish this message, let's say pane data username give it a try. Okay, so we've got the form that we came up with before. If we click join, that navigates us, and you can see there was kind of a fade effect there, so that's another thing that Tribe handles for you. It gives you hardware accelerated CSS transitions out of the box. You don't need to write a single line of code to get that neat fade effect, and there's also, you get some sliding effects out of the box. You may have, GitHub used to have this really neat sort of, when you navigated from a folder to another folder, it would slide across the page, and it was really quite pretty. I don't know why they got rid of it, but these are things that Tribe gives you out of the box. So let's bring up let's also join that channel, but we're going to join as anonymous too. There we go. So we've still got our message distribution, a little bit more functionality added in there, and I've shown you the navigation side of things. I'm going to cheat a little bit here, and I'm going to use a sort of a pre-built copy, but I'm going to introduce the concept of a saga. I don't know if people have come across the concept of a saga before. There's an integration, an enterprise application pattern called a process manager, and a saga is basically an implementation of that pattern. But what it allows us to do is maintain state across a long-running process. It may be 10 minutes, it may be never-ending, but basically we can just handle these messages that we're publishing and update state in our saga and have that state persisted for us. End service bus and a couple of other message buses around there. Around the traps give you sagas out of the box. I think Rhino MQ gives you sagas out of the box. So we're going to look at an example of So I'll start that one up. Now, what does a saga look like? So basically, we've got a similar sort of method that we need to call to register that saga with the framework. But basically, all we really need to declare is what data does that, what state is that saga capturing, and what messages does that saga handle. So you can see, I wanted to add a few more to this, but unfortunately I ran out of time. But this saga simply handles a chat message, and it pushes that message onto our messages array. And if we look at some slight changes to here, instead of having our own messages collection, we're doing this thing here where on our channel, we're calling join saga. And what join saga does is it goes off to the server and checks whether that saga has already been started. There's an alternate called start saga, which we can call, which will actually start a saga. It'll assume that there won't be one, and it'll replace any saga that exists with that ID. So the ID that we're creating it with is this pane data channel. That's the ID, and that's the saga type. So we declared our saga as a chat saga, so that's how we reference that. Now, join saga is an asynchronous method, so it won't actually return us our saga immediately. Start saga, on the other hand, is synchronous, so as soon as we call start saga, it will return us that saga object. What join saga does is return us a promise. I don't really have time to go into the promise pattern, but basically the promise ensures that this operation will either complete or fail, and when we want to access the result, if it succeeds, we just wrap it in this done function, and you can see it passes in our saga here. So then we're ripping out the messages out of that saga, and we're assigning them to a property on our view model. So let's have a look at what that looks like. It's going to look pretty similar. But wait, there was a message there. So if we publish some more messages, if we now refresh our page and we rejoin, those messages against that have been handled by that saga have been persisted for us automatically. We can now access that same saga from another client. So that saga has been persisted, and we can just simply retrieve that saga from anywhere. So that'll go and retrieve the state of that saga, and it'll set it up so that that saga will then handle the messages that are published. So how does this work? This saga is actually executing both in both of these clients. So these clients are handling that message, but there's actually a server process as well that's running where that saga is actually executing on the server as well. So basically, it grabs the data that's stored for that saga, creates the saga with that data, handles the message, executes that message handler, and then persists our data back to our persistent storage medium again. There's a little bit more work that needs to be done in terms of, I'll set it up to operate on the epochs that we talked about before. There's every chance that in the time that we've actually gone and retrieved that saga, that data, that people may have published more messages. So we can just simply take those messages that people have published and just send them onto this client. It's very simple to achieve that kind of epoch situation that we were talking about before. So it's a very brief description of sagas there. Once your processes start to get a lot more complex, this is a very neat pattern for maintaining your state across long-running processes. I'd like to show just a couple more little tricks with Tribe, and specifically on the composite UI side of things. Let's run in. I'll start that solution up. So in this one, instead of navigating, what we're going to do is we're just going to dynamically add a new pane to the screen each time we click that join. So instead of calling navigate, we're going to call this method append node. So let's have a look and see what that looks like. Oops. So if we now join that, it's simply appended that new pane that it's instantiated to the same screen. So we can join a second channel here. Now let's look at our other client. We'll join those same channels and see what happens. So if we refresh that, let's join, actually, I'm going to make it anonymous 2, and we'll join the same 2 channels. So there we've got good separation of there's probably one last little thing that I'd like to show you that's along the composite side of things again. If we wanted to break our chat pane down into 2 separate panes, it's really quite trivial. We can just simply create, I might actually just copy that. We're going to call that messages. So we don't want we can remove all of the stuff that's associated with our other section of it. And we'll remove the messages side from our chat pane. So we can remove our initialize and our channel. So now, instead of I'm actually going to embed it in here. We can simply say div data bind pane messages, and we need to pass in I'm not actually going to this is one I hadn't rehearsed. So basically, I mean, it allows us to break our panes down. If we want to decompose our panes further, we can simply take out the logic and the markup and the CSS for those individual parts of the pane. We can just split that out really simply into a separate pane. And all we need to do is just create these files. The framework handles all of the resource loading, all of the object lifecycle. Actually, one thing that's definitely worth mentioning is the cleanup. Oops. Shit. Now I've broken it. Aha. Shit. Sorry. All right, so we've set up all of these subscriptions on our pub sub engine. We've set up, we've actually called pub sub subscribe, and what that will do is that the pub sub engine needs to retain a reference to the handling function, which means we can introduce potential memory leaks. If we don't remove that subscription before we remove these elements from the page and forget about them, then we're going to introduce memory leaks. Our pub sub engine is still going to be referencing that function. What Tribe will do for you is the moment that a pane is removed from the DOM, it will automatically clean up all of your subscriptions for you. So you get automatic lifecycle management for your objects. And we give things, some helpers in there for handling things like subscribing to document events that it'll clean up that for you automatically. But it's an extremely powerful concept, handling your object lifetimes and not having to worry about the cleanup, because otherwise you, in a single page application where you're not refreshing your page every time you want to display something else, if you don't clean up your resources, you're going to get memory leaks. So this takes a huge weight off your task as a developer. To make your life easier. So that's about it. Any questions? Yeah, you need the microphone. It's not working. Microphone? It's not working. Or maybe, yeah, maybe it's got a... Yep. Shoot.
Yeah, in the choice of any framework, it's really about the extension points, because you're never going to do everything that anybody wants.
Absolutely.
So how have you handled that?
So Tribe does not preclude you from using any other third-party library that's available out there today. You can, I mean, currently it depends on jQuery and Knockout. If you want to use jQuery UI, if you want to use jQuery mobile, if you wanted to use underscore, you can just simply include these as dependencies for your application and it'll load those up for you. The framework itself is quite extensible. It actually has a rendering pipeline in it where every time you render a pane, it goes through a set of steps. So it'll load up your resources. It will select your template. It'll render that. It'll then perform your data binding, et cetera, et cetera. That whole process is extensible, and I've tried to make it as extensible as possible. So you can actually add new events into that rendering pipeline if you'd like, similar to what MVC does. Does that answer your question? Cool. Anyone else? Yo.
Obviously, it's using CQRS for the messaging the pub sub. If you weren't going to use that, would Tribe still be useful?
You don't necessarily need to use CQRS. It's kind of intended to facilitate CQS architectures. You don't necessarily need to use CQRS. A lot of the work over the next couple of months is going to be put into the server side, and we're going to give you the ability just to simply, if you publish a message on the client and you just want a certain action to happen on the server, update your data, then you'll be able to just write a simple message handler on the server to handle that. So you get your sort of your asynchronous. And obviously, like request response, you still need the request response paradigm in your application. If you're authenticating a user, it doesn't really make sense to publish a message to say, this is the username and password, oh, let's hang around and wait for our response. You still need that request response as well. But certainly for any sort of user commands that you're executing, it just gives you the ability to publish that message. And one of the things that we're actually aiming to do on that, the sort of prioritization is actually to spin off additional instances that will handle a specific queue of messages, so that you can then assign your resources to those. So it doesn't have to be CQRS. You can sort of use any event sort of message-based architecture that you like. Any other questions?
Did you think of moving the pub sub into the framework?
The pub sub is part of the framework.
But you still have to call. You have to call the setup. You could make it automatic.
What would be automatic?
So you automatically, basically, you have an object that changes, and other instances of the app would be able to.
Well, this is what Saga's handle for you. I think I see what you're saying, in that you kind of want to synchronize your object across multiple clients without having to worry about messages. The messages,
HLA framework does, yeah.
The messages are the important thing for the main reasons that we talked about before. We really want to be capturing the user intent. We need to give these messages that we're publishing, we need to give them specific meaning to be able to replay them on another object.
You could have view model objects that would then automatically publish on.
So what are you going to publish when the user changes? Are you going to publish the whole object each time?
Yeah, that's it. Yeah, I mean,
Yeah.
yeah.
I mean, really the whole idea is around capturing your user intent and breaking your application down into user transactions is really what you want, so the point that you sort of want to arrive at. Anyone else? Questions? Cool. Well, a couple more things. I did have a bunch of stuff here, but I was itching to get into one of the big things about Tribe, particularly because it's pure JavaScript, client and server. Originally the server was SignalR. What you'll find on the Tribe.js website at the moment is that the release does operate on a SignalR backend, but all that does at the moment is basic message distribution. You can actually plug into it and you can publish these messages onto an end service bus, message bus, but we're actually moving away from that. We're moving to a Node.js backend, mainly because it's pure JavaScript. So we can write JavaScript for the client that executes on the server as well. There's no additional overhead in terms of learning two different languages. You can use the same testing frameworks, etc. But certainly running JavaScript both on client and server is a very powerful thing, but JavaScript in itself is inherently incredibly testable. We can just use standard JavaScript unit testing techniques. We can unit test our view models very simply. Tribe gives us a way of instantiating an instance of a new view model. You can also integration test your pane, so you can actually create an instance of that pane within your browser and then look at the DOM, the HTML that it actually generates and test those properties, so we can integration test our panes very easily. And I'll show you a little example. So yoursports.net was actually written in a very early version of the composite part of Tribe. It used to be called knockout.composite purely because it was built on Knockout. But I think so what's actually happening here is that this whole user interface is being automated. And there's actually a DSL behind that where you can simply just say click, wait for pane to load, etc., etc. And this is really cool because we can just deploy this to anywhere, hit that site, hit that page, and those functional tests will operate in the context of where you deployed it to. So you can actually deploy your application to your production environment along with your functional tests, run your functional tests, and you get immediate feedback in your production environment that all your functional tests are passing. So the testability of JavaScript and web applications in general is just freaking awesome. So as I was talking before, there's the Node.js is not at a release stage yet. We're looking just to finalise the API and the semantics, add some more persistence mechanisms. We'll implement those worker nodes that we were talking about before, and various other scale-out sections. We need to introduce some bit more testing helpers. And one of the big things, one of the goals of Tribe is to make deploying your applications to mobile devices as simple as possible. So, I mean, there's a lot of HTML5 on mobile devices. That's quite popular these days. Basically, you can take the same panes that you develop for your web application, and you can just simply deploy those to your mobile device. There is only one skin at the moment, which is an iOS 5 skin. We can actually see that on the Tribe.js site. So this is the skin that it gives you, and you can just simply write really basic, the same way that you would develop your application for the web, and you can simply deploy it to a mobile device. I mean, obviously it's not quite that simple. You need to make sure that the layout and your HTML is going to display nicely in either, but it makes your life a lot easier in that regard. I've been thinking a lot about dependency injection. Angular, which is an alternate single-page application framework, actually gives you dependency injection. Some would argue it's not as valuable in JavaScript, but there are certainly benefits to it, and that's going to be a really cool addition to the framework. So that's about it. If you want any more information, please drop me a line either by email or on Twitter. If you want to have a tinker around with the code, it's all up there on GitHub. If you want to look at the current production version that the website refers to, you'll need to look at the release, because that is the master branch has the Node.js stuff in it as well. So if there's no more questions, got one more? What? Node.js is meant to be a dog. Depends entirely on how you develop your application. Yeah. Oh well, thank you very much.
Did you get all that? We'll take the SSW TV quiz and test your knowledge now.